All right, everybody. So it's time for part two. Just made part one, just uploaded it. Now on to part two. So this time I'll focus on, I guess every part I'll just focus on one thing. All right. And this time it will be equations that have exceptions. Okay. And that, if I got right to the point, I don't think it's that hard to understand. But I need to, or I think I should, encourage you to think about this a little bit deeper than you want to, okay? Because it's pretty easy to just hurry through things and just kind of take the bare minimum away from it. I'll try to discourage that from you as much as I can, all right? You might not like it, but that would be the right thing for me to do. So before I actually tell you what's going on with equations that have exceptions, I want you to think about algebra and what turns out to be calculus in terms of numbers. Because when I write, like if I say, is this true or false? Is x times quantity y plus z equal to x times y plus x times z? Is that true or false? Well, that's really makes no sense on its own. Equals, that's a math concept. And equals deals with numbers. Like numbers are equal. So unless you tell me what these numbers are, really there's no way to determine if it's true or false. Okay? All right. So, math deals with numbers and not letters. All right. Why do we use letters? Well, because we have these things called variables, which can take many values and so on. But we are dealing with numbers, and so if I ask you, is this statement true or false, to really know if that statement is true or false, we would need to consider what numbers the x and the y and the z can be. Okay? So for example, here's what I mean. What if I let x be 2, y be 3, z be 4? Then this statement would look like this. And then I can definitively tell you whether it's true or not. Okay, so here we go. I'm going to split it down the middle along the equal sign and say, all right, what's 2 times quantity 3 plus 4? Well, we do the order of operations. We say 3 plus 4, that's 7, and then 2 times, that's 14. Okay. And then on the other side, I work that independently, and I'd say, well, 2 times 3 is 6, and 2, 8, and I add them, I get 14. I get 14 is equal to 14. That's a true statement, right? Of course. Now, it turns out that it's not just that I got lucky there. It's not like I just chose by accident numbers that happen to work. This statement is true for all numbers x, y, and z. It doesn't matter what x and y and z are. This will always be true, meaning you can evaluate and test it just like this, and it will be true every time. So because of that, there's a name for it. It's called the distributive property. Since it always works, since at the end of the day, everything here's got to be a number if we're doing math, and since this always works, we have a name for it, all right? Okay, no doubt, if you're in calculus, you've seen it before, you maybe even remember the name, but I want you to start thinking of it in terms of numbers and whether something is true or not. Okay? All right. Now let's look at another one to compare with. What about this one? Is that true or false? In calculus, I see lots of people do stuff like this. Let's say root of one number plus another is root of the first number plus root of the second number. It seems like it might be true. If you don't know any better, it doesn't look wrong. So let's try it out. Let's put numbers in. That would really be the only true way that most people can understand if this is correct or not. All right. So I'm going to take that statement, and since we're doing math, I'll do this crazy thing. I'll put numbers in and see if they work or not. Right. I'll let x be 1 and y be 0. Does it work? It actually does work. See, okay, root 1 plus 0. Okay, 1 plus 0 is 1. Root 1 is 1. Okay, on the other side, root 1 plus root 0, okay, square root of 1 is 1. It's true, it worked. But would it always work? Does it work sometimes? let's compare. Let's try 4 for x, 9 for y. Okay, so I'm going to take this statement, 4 for x, 9 for y. It would look like this. 4 plus 9, 13. Root 13 is about 3.6. On the other side, root 4, root 9, 2 and 3, 5. Well, it doesn't work. So, like, maybe it works sometimes, but not all the time. Or maybe this is like the only time it doesn't work. Okay? Or maybe this is the only time it does work. Sorry. So that's my point with this one is it's questionable. You know, it doesn't work all the time. It works some of the time. What are we going to say about it? Okay? What should we say about this? I can show you that it's sometimes true and sometimes false, but let's do this. Here's our bottom line about it. We'll say root x plus y is not equal to root x plus root y. It's not generally true. Okay? So don't do it. You know, if you're at some point later on taking a test or something and you get this, you might be tempted to simplify it into that, but it doesn't work, okay? It's very easy for this statement to be false, all right? That's all I'm trying to get you to see. And don't do this either. If you're working the test at some point and you're dealing with root 1 plus y, don't reduce it to that. Don't say it's root 1 plus root y, because it's not, all right? It probably won't work. Okay, all right. Okay, why would I tell you this? Well, just because that I need you to see that the only way that this really has meaning for us is for the x and the y to be numbers. Math is about numbers, okay? And then you can agree with me, because I showed you some calculations, that it's not generally true once you put numbers in. And so we don't do it, all right? Okay, so now, all right, here's the problems in the lesson actually start to look more like this one. Okay? But I think to understand this one, we have to have done what I showed you just a minute ago. All right? So everything I showed you so far leading up to this. Is this true or false? Is x squared minus 9 over x minus 3 equal to x plus 3? Is that true or false? Now, I think it seems like it's true. Why? Well, because you can take that top thing, x squared minus 9. You can factor it. It's the difference of two squares. And you'll get x plus 3 times x minus 3. And then you'll cancel those. Everybody likes to cancel. I mean, if there's one thing I know from teaching math, it's that people love to cross stuff out. All right? So x minus 3, yeah, cancel. You get x plus 3, right? Okay? It seems true. But really, is it? Like, so here's a challenge for you. Just take a minute and think about this. Can you think of a number that if I were to put it into this statement, what you get on this side would not be equal to what you get on that side? Can you think of a number that would make this statement false? Okay? That number turns out to be 3. Okay, so let me show you. Let me show you the reasoning behind that. So first, I'll demonstrate that it doesn't work. So if I were to put 3 for x into this statement right here, okay, here's what it would look like. 3 squared minus 9, 3 minus 3. That's 9 minus 9 over 3 minus 3. That's 0 over 0. That's undefined. On the other side, if I were to put 3 in, I get 3 plus 3. I get 6. Well, is this equal to that? Definitely not. Okay? So yeah, that does seem true. I mean, you can factor and cancel, and it seems like you can reduce it, but remember, my theme in this lesson is that everything is a number at the end of the day. It's math. I don't look at that like it's an x. I look at it like it's going to be a number, and I have to think about all the consequences of that. Okay? So, all right, yes, so the 3 does not work. Okay? Let's try to think about why it doesn't work a little bit. So here's something else I need to get you to realize. Remember when up here I said, well, we could take this and we can factor it and we can cancel. What is canceling? Canceling is division, right? It's like we're saying A number divided by itself is 1. That's really all canceling is right here. But what are you canceling if x is 3? What's 3 minus 3? 0. What's 3 minus 3? 0. Does 0 over 0 cancel to 1? Definitely not. Okay? You can't cancel 0 over 0. So when you cross that out, you got to think, well, that's going to be a number. And if the x happened to be 3, this canceling wouldn't be possible. So you can't get from here to here if the x is 3. That's why the statement didn't work when the x was 3. All right? Okay, so there's all the different sides of that. Now, you might be thinking that I'm overthinking this. I'm making it too complicated. You're free to think that. Think about it however you want to. This is what the depth I think that you should see, like it or not. But let's do this. Let's reduce it to a principle. Let's say, well, maybe I am overthinking it. Is there just some principle that I can tell you and you can just think about it like that? Well, yes. Okay. So here's what I've established in that last problem. If we reduce a fraction, values for the variable that cause 0 over 0 will be exceptions to our result. So what that means is this statement is false. Why is that? Well, I just showed you that if you put 3 in, this and that are not the same, right? Yeah, I proved it. If you go here and you start plugging in numbers, I can't guarantee you that that's going to be true. This statement's true, though. X squared minus 9 over x minus 3 is equal to x plus 3 if and as long as you don't plug in 3. That is true. Okay, so that's the exception right here. Right? Remember I said values that cause 0 over 0 will be exceptions to our result. Yeah, you can reduce this to this, but there's my exception. Where did the 3 come from? Why is that the exception? Well, on one hand, it just doesn't work. On the other hand, it's the value of x that will lead to canceling 0 over 0. So those are the ways you can think about it. Okay, so false statement, true statement. Okay, but here's our guiding principle for reducing and making statements about this kind of thing. So let's look at a few more, and for the next few, I'll just rely on this principle. Okay, so again, let me give you some statements and see if you can decide if they're true or false. So is this true or false? Is 3x minus 6 over 2 minus x equal to negative 3 if the x is less than 2? Is that true or not? Okay. Well, let's try reducing it. Because maybe you could reduce this down into that. Let's see what we can do. I can factor out 3. Okay? And then I get x minus 2 over 2 minus x. And those aren't the same, so I can't cancel them. But then I could factor out a negative 1 here, like so, and then they are the same. And I'll cancel them. Well, can I really cancel them? What are you doing when you cancel? You're dividing? Are you dividing x or are you dividing a number? I mean, that's got to be a number, right? What value of x would cause you to be canceling 0 over 0? 2, right? 2 minus 2 is 0. 2. Yeah, you can't cancel here if the x happened to be 2, so that has to be an exception to our result. So let's say we'll cancel it as long as x is not 2, and then otherwise we'll get 3 over negative 1, so we'll get negative 3. Okay, so here's our reduction. There's our work. There's our statement. Here's our exception, right? I mean, it's all based on this principle that we reduce a fraction. Any value that causes 0 over 0 as we reduce it will be an exception. Yeah, so 2 is that number. Now, if this is true, is that one true? If this reduces to that, as long as x is not 2, can I say that this will be equal to this if x is less than 2? Well, think about it. Does this condition include the number we must leave out? No, it doesn't. Okay? So since it doesn't, it's a true statement. All right, so there's my final statement about this one. Yes, it's true. This will reduce to that as long as you don't plug in 2. And if you're just restricting yourself to be less than 2, that won't happen, and it's guaranteed to work. Okay? All right, so let's do, how about this? Let's see just a little variety. I'll take the same one, okay? And I'll change the condition a little bit. Is this true or false? Will 3x minus 6 over 2 minus x be equal to negative 3 if x is anything bigger than negative 2? True or false? Well, so we already determined that this reduces to this as long as you don't plug in 2 for x. But this condition does include that number that's not allowed, doesn't it? I mean, this says if for any value more than 2. That's how I would read that. Anything more than negative 2. Well, that would include 2, and these aren't equal if x is 2. All right, so that one's false. Just taking it at face value because of this, because that condition would include that number that we have to leave out. Okay, so, all right, now I got some mileage out of that one. I showed you 2 examples that involve that. So let's look at one more, okay? So I'm going to play on the same theme where I'm going to use this principle. If we reduce a fraction, a rational function, if you use the precise terminology, any value for the variable that causes 0 over 0 will be an exception to our result. So here for this one, it's like I have something that's kind of partially given to me. It says, well, this will in fact reduce to that, so long as the x is not some unspecified number. Can you tell me what that number has to be so that this statement is true? Okay. All right, well, let's see. First, I guess we would have to prove somehow that you could reduce this to that. So let's try to do it that way. Let's reduce it. So here's what you start with. X minus 2 third power. Okay, 3 factors x minus 2. And it happens that x squared minus 4x plus 4 factors as x minus 2 times x minus 2. Now, when you cancel these and these, because they're all the same, well, what value of x would cause any of this canceling to be 0 over 0? It'd be 2, right? Okay, so you could reduce this to this, all right, x minus 2, as long as the x isn't 2. Because if the x was 2, you're canceling 0 over 0, and you can't do that. It doesn't work. It's not allowed. Okay, so 2 is the exception. So, all right, to give a formal statement of the answer, what should n be so that this statement at face value is a true statement? The n would have to be 2. All right. In other words, that number right there would have to be 2 for it to be true.